In this video, I'm going to talk about what a weighted average is and what it means, why it's important in chemistry. So I want to start with chocolate. When I was a kid, I loved Hershey's Kisses. But back then, we only had regular Hershey's Kisses, which tasted good, and almond Hershey Kisses, which were amazing. Nowadays, you got choices. Peppermint cookies and cream, special dark chocolate, even Hugs. But in my day, we only had Hershey's Kisses and almond Kisses. And so because I preferred the almond Kisses, when I became an adult, I could buy whatever I wanted. And I would buy a bag of Hershey's Kisses, regular, and then 4 bags with almonds. Take them home, mix them in a big bowl, and then distribute them into smaller bowls so that I could have Hershey's Kisses around the house. I had a bowl on the table by the front door, a bowl on the coffee table, a bowl on the piano, a bowl beside my bed. And each bowl had that ratio, 4 bags of almond Kisses to 1 bag of regular. So if I was to take a scoop with my hand, I would get 5 kisses, 1 regular and 4 almond Kisses. And so the natural abundance of kisses, kinds of kisses in my house, was 20% chocolate and 80% almond. So if I was to consider what is the average kiss, in my house, well, 1 would be chocolate and 4 would be almond. So let me add those together and divide by 5 to see what the average is. So if I have 1 kiss that's 4.8 grams and 4 kisses that are 4.2 grams, an average kiss has a mass of 4.3 grams. Now, is there any real kiss that has that mass? Not in this house, but it would reflect something about the average for our house. So there's a way to do that where we consider the natural abundance. So for the chocolate kisses, I could write 1 in 5, or I could say 20%, or I could use a decimal fraction. And that's what I'm going to use here. For the natural abundance, I'm going to use a decimal fraction. For the almond kisses, every 4 out of 5, 4 are almond, which is 80%. But again, I'm going to use a decimal fraction to reflect my natural abundance. Okay, and then I'm going to multiply it times the mass. So just plain chocolate would be 4.8 grams. And chocolate with almonds, 4.2 grams. So I'm going to multiply 0.2 times 4.8. And what do I get? Same idea here. 80% at 4.2 grams. So 2 sig figs times 2 sig figs, this number stops in the hundredths place. 2 sig figs times 2 sig figs, this number stops in the tenths place. And when I add those two numbers together, the calculator tells me 4.32, but my least precise measurement when I line up the decimals is the tenths place. So the average, considering the weighting of 1 in every 5 is regular and 4 in every 5 is almond, the average is 4.3 grams. And that happens in nature. We can apply that same idea to atoms. In nature, there are 2 naturally occurring isotopes of copper-63 and copper-65. Copper-63 is more abundant, and copper 63 has a mass that we know here to 4 sig figs. On the periodic table, we have information about copper. The name, the symbol that goes with that name, the atomic number, which is the number of protons, and then here we have a mass, and this is a weighted average. There is no copper atom that has this mass. Where did this mass come from? Well, it reflects the average, the weighted average of the masses of actual copper isotopes. So to get this number, we do that same process. We consider each isotope or kind. We look at its natural abundance in the form of a decimal fraction. We multiply that times the mass of an actual atom, a measured value. In this case, we're going to use atomic mass units. And then when we multiply that out, we're going to get the isotopic contribution from this isotope. That's a lot of words. So about 70% of copper is copper 63, and that contributes this much to the overall average. Let's do that same idea for all the isotopes, in this case 2. So for copper 65, 30% put into a decimal fraction looks like this. The mass of an actual copper 65 atom, which does exist, is this. And then here, we're going to have the isotopic contribution from the less abundant isotope. I will add these two together to come up with a weighted average to reflect copper's mass. And then I need to consider sig figs. Okay, so for sig figs, I have an abundance to 4 sig figs, a mass to 4 sig figs, and so this value, this isotopic contribution, ends in the hundredths place. For copper 65, 4 sig figs for the abundance, 4 sig figs for the mass, 1, 2, 3, 4, that value ends in the hundredths place. When adding and subtracting, we look at where the decimal is, we line it up, and we can only go as far to the right as the least precise digit. And then I round. So, to 4 sig figs, we have found the weighted average for copper, and that is what is given on the periodic table. On the periodic table, that value could have be reflected in two kinds of units. We could say that there are 63.54 atomic mass units per atom, and it's not a real atom, that's for a weighted average. Or we could say there's 63.54 grams in a large group called a mole, which we'll get to in a few chapters. So that's two ways that we can interpret the weighted average that we find on the periodic table. Using the number that we have on the periodic table, we could actually figure out what the isotopic abundance was if there were only 2 isotopes. So to do this, we're going to set up the equation in the same way. We're going to say the abundance of 1 times its mass plus the abundance of the other one times its mass adds up to the whole, which we find on the periodic table, the weighted average. So here we have one equation and 2 unknowns, and we can't solve that. There is a second equation if there are only two. X plus y equals everything. So I'm going to do a substitution. I'm going to say if x plus y equals 1, y equals 1 minus x. And I'm going to plug that in here in a substitution. I'm going to go ahead and just ignore these units for a minute because they're cluttering up my page. Okay, so now I'm going to need to distribute this. 1 times 70.9247 is 70.9247. X times negative x times 70.9427 is negative 70.9247x. Now we need to collect like terms. So I'm just going to bring this 70.9247 to the other side. I'm going to subtract it. And so I'm going to combine these two. And then I'm going to combine these two, but on the right side. And now I'm going to divide both sides in order to isolate x by negative 1.9991. Anything over itself equals 1. And here I got 0.60112. Okay, so 4 past the decimal, 4 past the decimal, 4 past the decimal. This is only good to 3 past the decimal, so this is only good to there. 4 sig figs divided by 5, 1, 2, 3, 4. And if I multiply by 100%, I get 60.11% is the percent abundance for X. %60.11%. And then Y is just 100 minus that. 39.89%. Okay, so those are the two kinds of weighted average problems that you could see. We could see one where we have to use a system of equations to solve for the abundance. And the second equation that we need was this one, x plus y equals 1. More commonly, you're going to see this. In our class, you're going to see this. I'm going to use the natural abundances and the masses to find the number I expect to see on the periodic table, which is a weighted average. And there is no actual atom that has that mass. Thank you for your time.